Hello there, welcome back. And what we are going to do now for few videos to come is explore the journey of how some text written in some file gets converted into binary zeros and ones, and how the machine executes it. And once we are done with that, we'll kind of have a good understanding of why there is assembly, why there is machine code, and why there is C. And then we'll jump into a little bit of assembly, and from there we go to the C language. Okay, so actually, before we jump here, what I wanted to mention was I have made some additions or edits to the README file, and there are few commands here, and there is a link to a PDF here that we are going to use for the next few videos, and I'll come to in terms of how to use all of this in a bit. All right, so let's go back now and recall essentially that we kind of had this model of the system where we said, hey, there is memory, there is CPU, and now what we're going to focus on is just the instructions part. So let me just kind of draw only that one path, which is, so we have got the instruction address bus, right? Let me just call it add here. And we have got the instruction bus, right? And so we reason that some part of the memory has the code, and the program counter from within the CPU, whatever number it holds, that is the location from which the instruction will be fetched. And then we said, hey, the instruction will be fetched into something called the instruction buffer, and the instruction buffer content will be consumed by the control unit. That is where we had ended, or that is where the models got us. Well, that's the model we have. Now, what I want to explore as part of this particular lecture is how the instructions are encoded, right? So we are going to explore as to what bit pattern means what. All right. Okay, so now the trouble is, in terms of doing that, that there are many architectures, CPU architectures. So what does that mean? It means that there is something like x86 systems, CPUs, there are ARM, then there is, RISC-V, right? So there are many different architectures, and each of these architectures provides a different encoding for the instruction. And we are to essentially kind of pick one of those. So I've decided rather, to go with the RISC-V one. And the reason to that is the RISC-V is open. There are a lot many forums that talk about it. And the specification is open. You can go explore RISC-V documentation. And in fact, the document that I have here is for RISC-V, right? And we'll jump into that documentation. And what I want to now do is introduce the idea of something called, we talked about architecture, but there is something called instruction set architecture. And what is instruction set architecture? It's also called ISA. So every CPU has an instruction set architecture associated with it. So x86, for example, x86 has an architecture, well, that's called the x86 architecture. So CPUs like, the Pentium, the latest ones, the Ice Lake, the Lunar Lake, and so on and so forth. Well, I don't have an Intel CPU around me, but the latest CPUs from Intel, so to speak, comply by the x86 and the AMD 64 architecture. So the architecture here essentially means encoding of the instructions. There is a specification that dictates as to how the instructions are to be encoded and how the CPU will understand or process those instructions. Okay, so we are going to take a look at or focus our work or these lectures on the RISC-V architecture, and we are going to focus on RISC-V, the 32-bit integer instruction set. Now, all of this might sound more or less like just plain theory, but here's the significance of the ISA. So recall that we reasoned that we do not want to understand or don't care about the implementation of the CPU, the circuits, the digital design of the CPU. We don't care about it. And what we care about is writing programs and getting that CPU to do something. So we are going to be in the software land, and we don't care about the underlying hardware. Now, the freedom to not care about the underlying hardware comes from the fact that there is an ISA. What does that mean? It means as long as I write my software and then convert it into bit patterns, the binary, so to speak, that is encoded as per the ISA, this particular hardware, which also complies by the same ISA, will be able to execute that code. And for those reasons, I'm free of caring about the details of the hardware, the implementation details of the hardware. So what does that mean? As long as people tell me, as long as from the market or from the internet, I order a CPU that is compliant with rv32i instruction set, and the fact that I have compiled my code, converted my text code here, which is either C code or assembly code, as long as I have compiled that into the rv32 instruction set encoding, if my instructions are encoded as dictated by the rv32 standard, then this processor that I ordered or got from the internet will execute my code. That is what it means. So you can think of the ISA as a contract between the software and the hardware. So as long as the software is compiled and complies by the ISA, the final bit pattern, if it is compliant with the instruction set architecture for the given processor, the processor will execute it. And that is one reason why you can, for example, have games and later on an x86 machine, and later you can go from, let's say, I don't know, Ice Lake to Lunar Lake, or i7 processor to some next version of the i7 processor. What happens is the underlying hardware has changed, but the ISA that it supports remains the same, the x86 or the AMD 64 architecture. And so your game can continue to execute. Your Windows software or Linux software can continue to execute on the same on the new processor, which supports the same architecture. That's very, very important. The hardware guys are free to innovate in the hardware land and change this circuitry as they like, but the only condition is the circuitry needs to abide by or respect the ISA. And as long as the ISA is respected, the compiled software, the binary, will execute on that hardware. All right, so this was like too much theory. Now let's dive into taking a look at the instruction set architecture for RISC-V. So there is this on our repository here, and if you have not visited the repository, I would kind of encourage you to go and take a look at github.com/pajamabra/c-language, and once you're there, look for the README, and somewhere in the README you will find RISC-V reference card, and just click on this download the PDF button, and what will happen is it'll download a PDF, and I'll go ahead and open that PDF, right? Okay, and then at this point I must also go ahead and kind of full screen. But how do I do that? Okay, the dumb person that I am, this is how you full screen it. Okay, so what we see here is the instruction set for the RISC-V. Okay, and this document is kind of rather long. It's 6 pages long, so digestible. You can go through it. And what I want you to take a look at and even internalize maybe as we go forward. Um, okay, the green color is not so much suitable. I'm going to try and change it. Let's see if I can. Yes, I managed to. Yes, okay, this one's good. Okay, so what we see here, first off, is there are some 6 types of instructions, right? And this is essentially um, what is dictating the, so to speak, the encoding of the instructions. You might not understand this if you don't have any familiarity with instruction sets um, just yet. It'll take kind of few minutes, but just stay with me. So what is happening here is we have got 32 bits, right? And then set of bits here, have meaning associated with them. So anytime the CPU looks at the instruction buffer, and recall we had the memory where there was instruction, and we are going to impose that the instruction is 32-bit wide. So that came into the instruction buffer. And so the control unit is going to now consume those 32 bits. And the encoding of this 32 bits, my claim is compliant or dictated by the table here or the encoding provided here, right? So what is this denoting? What is this showing us? So it's saying that there are 7 bits, 0 to 6, which is 7 bits dedicated to the operation code. So what is operation code? Well, operation code is the operation that the CPU should do. So things like add, subtract, multiply, and or shift, those kind of things. And there is like, a list of those here. And then the opcode is also listed. We'll take a look at that in a bit. Okay. Now we talked about the fact that the CPU has a register file inside, the GPR, general purpose registers. And we'll just say that the registers go from, let's say, X0 down to X31. There are 32 registers, let's say, right? And each one of them will have an address 0, 1, 2, 3, so on and so forth to 31. And the internal register file has the circuitry to figure out, what registers to use. Okay. So the destination register, so for example, when we do C equals to A plus B, so you can imagine that this is the destination, this is an operand, and this is an operand, right? Or this is the source 1, this is the source 2. So similarly, we can perform, let's say, addition on 2 registers and put the answer in third register. So the third register would be the destination register. And if you see 11 down to 7, so 11, 10, 9, 8, 7, so 5 bits are representing the destination. The interesting part here now is the 5 bits can help us represent 32 registers or 32 numbers, and that is how we go from the 0th register to the 31st register, right? So everything here kind of makes sense and is designed on purpose. Right. Then they have left some 3 bits for function 3, which will come to in a bit. Then there is source register 1 and register source 2, right? So C equals to A plus B. So this, let's say, is RD. This is RS1. This is RS2. And this plus will be represented by the opcode, right? And if none of this is making sense so far, again, go back, watch this multiple times. But the understanding of this is going to make you an absolute ninja when it comes to writing C code and reasoning about what the machine would be doing. Now we have again chosen a machine which is RISC-V, but kind of the same kind of reasoning applies to all the architectures. So all you have to do is figure out the instruction encoding for a particular architecture, and you can literally look at zeros and ones of an instruction of a memory and then be able to tell what kind of instruction it would be. I never had to do that, but if you want, that is possible. Okay, and we'll also explore the tools that help us do that, by the way. Okay, So, and then the function 7 is essentially, we'll come to that in a bit. So function 3 and function 7, so these are the 3 bits here, and these are how many? Well, some 7 bits, I guess. So 7 bits here. So the idea is, given an opcode, so for example, if you have an add instruction, you can have variants of the add instruction, add with carry, add immediate, those kind of things. And the variants are denoted using these extra bits here. That's it. That's the only purpose that these bits have here. Now you could argue as to why they have taken and so to speak, separated 3 bits here and 7 bits here. So the background to this is the RISC-V ISA designers, they wanted to make the implementation of hardware simpler or easier for the designers. So what they have done is, in most cases, they have ensured that different common things uh, are placed at the same bit position for different instructions, right? So the 6 things here, which I didn't talk about, so these 6 things are the 6 type of instructions, right? So this, for example, is a jump instruction. So a jump instruction would be encoded like so. A register instruction would be encoded like so. An immediate instruction is encoded like so. I think this stands for signed, unsigned, and branch instructions, right? So these are like the different type of instructions. Fence is something we'll come to later. If you want to look up, it has to do with something called memory barriers. But nonetheless, we'll come to that later. And now what I want to spend time on is this thing right here, right? So we are going to follow or focus on the rv32i instruction set, which is the base integer instruction set. And what it means is, for any CPU to claim that it is RISC-V CPU, it has to implement the base integer instructions at least, right? That is the kind of the precondition to calling a CPU, or a CPU designer calling it a RISC-V CPU. All right, so what are things of interest to us here? Well, first off, okay, there is an add instruction, and this is just kind of the friendly name for the instruction. And so there is opcode, which is like so. The function 3 location will have a 0, the function 7 will have a 0, and this is the operation it represents, right? So now if you were to hand code, and let me, well, why is this not moving? Okay, right. So if you were to place these bits in this location, then let's say we were to put 0, 1 here, we were to put a 0 here. I mean, we have to make all the bits 0. And then if we were to put like a 2 in binary in this location, put like a 3 here and 0 here, we would have essentially conveyed or written, encoded rather, R1, R2, and R3. It essentially means, hey, the opcode is for the add instruction, the RS is register number 1, so X1, and oh sorry, I should have written this way. Yes, in RISC-V the register names start from X, in ARM they start from R. And we'll see that also, by the way. Okay, so add x1, x2, x3, it means x1 equals to x2 plus x3, right? And this is how we'll go about encoding them. Now again, this is getting a little longer, but I just want you to have familiarity with what an ISA is. And trust me, it becomes very interesting when you're dealing at the bits level and instruction and writing assembly. Okay, so these are then the different instructions that we have. There is add, subtract, XOR, OR, the encoding for them. And you also have like the format that this instruction follows, right? So we have this shift and other instructions which are immediate type. Now the immediate type instruction would be an instruction, for example, add x1, x2, 10, right? So this essentially means, hey, this number 10 here is part of the instruction itself, right? And that is where we have this immediate, so 12 bits dedicated to storing 10. Now, something like this, the details of the ISA, is what will let you kind of, or rather, is what will enlighten you to the fact that you cannot have an immediate number here which is beyond 12 bits. The number has to be represented by 12 bits because in the instruction there are only 12 bits dedicated to it, right? Similarly, the jump instruction has, I think it can represent maybe 21 or 20 bits, I think, right? It goes from 20 down to 1, and that is just 20 bits. Or, you can count and let me know if I made a mistake there. All right, so we'll move on, and we'll obviously, make sense of all these instructions in due time, but the encoding is present here. So if you see here, this I think is it the short or the signed, instructions, and then there are unsigned instructions, and then there are branch instruction, branch on equal, which compares two registers, branch on not equal, less than, greater than, all of those, right? Then there is jump and fence and so on and so forth. All right, so this is about the instructions, and there are other instructions also which we won't take a look at least not right now, which is if your processor happens to be rv32mi, let's say, so it supports the integer instructions which we just took a look at, and it also supports the multiply extension, right? So that's the M here. And then these instructions are extra. That machine is capable of executing these instructions. Now, again, the lecture is becoming a little longer, but stay with me, and this all will, trust me, this all will pay off, multi-fold. Similarly, you have got floating point related operations, instructions related to that, and then we move on. There are compressed instructions. There are pseudo instructions. Pseudo instructions are fake instructions. So which will kind of come to later when we are writing some assembly. But the idea is that the single instruction of assembly will decompose into these instructions right here, right? And again, what it does, we'll take a look at later. Then what I wanted to show was the registers that I was referring to. So recall the program counter, the general purpose registers. So essentially, these are the general purpose registers, and we go from x0 down to x31. Now they have friendly names also based on their general usage, and those are these. And then there is some description about what they can be used for, right? And we'll come to the usage, why they're named the way they are much later. If our CPU is having floating point capabilities, then these are the extra registers for floating point operation that we get. Floating point operation is decimal operation, like things like 1.5 into 2.5, those kind of things, or 1.5 plus 2.5. Okay, what I want you to note here, and that's like the last thing I'll show you right now, is the x0 register is a hard coded 0, which means if you want to use a 0, x0 is the register, right? So if we did add x1 comma x2 comma x0, it essentially would mean x1 is equal to x2 plus 0, and well, it's essentially x1 is same as x2. Now you could ask, hey, why have like a register dedicated and hardwired to 0? When turns out, when you're wanting to move value from, this is for example, right? When you're wanting to move a value from x29 to x27, you could either use the move instruction, or you could simply just say, hey, add x27, x29, and x0, right? So there are a lot of instructions which can benefit from having a hardwired 0, and this is exactly why we have the X0, right? All right, so with this long lecture, what I'm hoping that you took away is we are going to work with the RISC-V CPU. This is how the instruction encoding for it is. Uh, we don't have to be aware of all the instruction encoding, but what we will use is that these are the things, now these are the instructions that are available to us, and we are going to write our assembly program using these. So in the next lecture, what we are going to do is we are going to explore the tool set, the utilities, and kind of the toolchain entities like compiler, assembler, linker, so on and so forth. We're going to explore those and see how a program can be written in assembly and how it can be converted to binary. So with that, I'll see you in the next one.